In this section, we're going to be talking about confidence intervals at the beginning, and then more specifically, we're going to be talking about confidence intervals for the population proportion toward the end. When we talk about confidence intervals, basically what we're trying to get at is estimating the true population value. So for a confidence interval, we usually abbreviate it first of all, CI. So this is probably the last time we'll ever write out confidence interval. So here's CI. The general form for any confidence interval is going to be my point estimate plus or minus my margin of error. So my point estimate plus or minus margin of error. Now what the plus or minus means is I take my point estimate and subtract my margin of error. That's on one end. And then I take my point estimate and add my margin of error for the upper end. So this is a general form for any confidence interval that we'll be looking at it for the entire class. Now, depending on what type of point estimate we're looking at, whether it's p-hat for the population proportion or the mean, we'll change the specifics of this, but this is a general form for every single confidence interval. Now let's go ahead and remember what point estimate means as well. The point estimate is a single value, so just one number. So it's a single value that estimates the population value. Now more specifically, it is a statistic. Remember, a statistic is based on a sample that estimates a parameter. Remember, a parameter is based on a population value. Now, coming up with the population of values and then actually determining every single value taking a census is very difficult. So instead of doing that, we sometimes take a smaller like a subsample of the population, and then we take that information from our sample, and if it's well collected, it will do a really good job at estimating our population parameter. So point estimate is going to be an important definition to know, as well as the general form for a confidence interval. And then we'll also talk about some specifics here. Now, for a confidence interval, when I build a confidence interval, it always goes in terms of a small number up to a large number. It never goes large, comma, small. It's always small to large. This is the same as you'd read the number on the number line. So left to right, small to large. Now, what is the nice thing about a confidence interval? Well, there's a lot of nice characteristics. One example that we could talk about is estimating. So for an example here, I could be looking at, let's say, car A and car B. Now they all have window stickers and they always give the estimated MPG for the city and the highway. So for that, let's say they tell us that the average miles per gallon, and this would be X bar, it's based on a sample, is let's say 28.2 for both cars. Now if you were buying your car only based on MPG and nothing else, it looks like that these cars are equivalent. They look like they're the same. Well, this is just our point estimate. It's just a single value that estimates the true mileage for all of these types of cars. Well, let's go ahead and talk about a confidence interval then for each of these. So for my first one, let's go ahead and say our confidence interval goes between 23.2 MPG all the way up to 33.2 MPG. Okay, so that's informative. Let's go ahead and look at a confidence interval for our second car. So for our second car, let's say it goes down to 10.2 for my lower bound, and then for my upper bound, let's say it goes to 46.2. Now, if I was going to purchase my car based solely on this information, it looks like the car A is a lot more consistent with its mileage. It only ranges plus or minus 5 miles per gallon, whereas this one has a wildly ranging miles per gallon. Car B goes clear down to about 10, clear up to 46. And so if you wanted consistency in your mileage, it looks like car A would be your option. If you wanted inconsistency in your mileage, it looks like Part B would be your option. And of course, there's a lot of other things going on in here as well, but that's just a good kind of quick explanation about what we use confidence intervals for. They provide more information about a point estimate other than just that single value. Now, when we talk about confidence intervals, let's go ahead and look at another example. Let's go ahead and talk about the example where we have, let's say, a confidence interval that goes from 18 to 24. Well, we can go backward on this and come up with our point estimate plus or minus on my margin of error. Now, a lot of times when we hear about surveys being taken about, let's say, a presidential primary or something, they'll say, 48% plus or minus 2 points or something like that. So this would be an example of where something like that might come from. Now, we can work backward to try and come up with that margin of error and the point estimate. The point estimate is the middle. It's halfway in between 18 and 24. So to come up with our point estimate, we would have 18 plus 24, the sum, divided by 2. So if we take 18 plus 24, I get 42, divided by 2, I get 21. So my point estimate is 21. It's halfway between 18 and 24. So the way I get that is I average those two values. Now, to come up with my margin of error, I just look to see how far is it from 21 to 24 and how far is it from 21 to 18, and it's the same number. In this case, it's 3 points. So 21 plus or minus 3 would be where this confidence interval came from. So that's one of the neat characteristics about a confidence interval. If it's given to me, I can work backward and come up with my point estimate and for my margin of error. Now, I didn't really say what this confidence interval was, but we'll just say this one's based on an average, even though we're not going to actually technically look at averages until the next unit or the next lesson. The same idea will work for proportions as well. Now, when we talk about the margin of error, there's a couple of different characteristics that make up the margin of error. So the point estimate is pretty straightforward. It's just a quick little calculation for our statistic. But this margin of error comes into play with a confidence factor and then some sort of standard error or standard deviation of the mean or standard deviation of the population proportion. So that's another interesting part here, is the margin of error actually breaks down into two things here. We have a confidence factor, and then we have some sort of standard error. Now, when we start talking about confidence factor, there's a couple of interesting characteristics. As confidence increases, meaning I'm more and more confident about this interval, my interval has to get wider and wider. So the width increases as well. And of course, that just basically means the margin of error increases because the width increases. So if I want to be 100% confident, let's say, in estimating a student's IQ, I could be really good at that. I could say, oh, it's somewhere between 0 and 500. Well, it's not very accurate or useful, but it is 100% confident that the student's IQ will fall in that range. Now, if I'm less confident, if my confidence goes down, let's say I'm only 90% confident in my estimate, what ends up happening is the width will decrease as well. So I might say, well, I'm going to go try and estimate your final exam grade right now before you even take it. I can do that. I can say, well, I think it's going to be somewhere between 70 and 80. But I can say I'm only about 60% confident with that. So that tells you that I'm really not that confident, and so that means my width can decrease because I'm not very confident about it anyway. Well, if this happens, the margin of error decreases as well. So these are some good things to know about a confidence interval. Now, as we start talking about specific confidence intervals, we'll talk about some more characteristics as well. Now, with the confidence factor, what ends up happening is you can use different tables. The only table we know right now is called the normal table. Before this is out, before we learn the next couple of types of confidence intervals, we'll also be learning about a t-table. So let's go ahead and talk about confidence intervals using the normal table. So if you have your set of normal tables, that would be good. So let's say I want to be 80% confident in my estimate. Well, let's go ahead and look backward and see what that 80% confidence kind of looks like. And again, I'm assuming normality here. So if we talk about the normal distribution, I know the mean is 0 and the standard deviation is 1. I'm going to work backward from there up to my data that's being given. So the mean is 0. Well, if I'm 80% confident, and that confidence is going to be centered around the mean, 0.80 would lie on either side of the mean. Okay, so 40% above, 40% below. Now, because of this is symmetric, what ends up happening is I have 20% that does not lie in here, and I have to split it between the two tails. So this is 0.10 on either side. Now, if I add up the 0.10, 0.80, 0.10, this adds to 1.0. And remember, that's the total area underneath the curve, is 1 or 100%. Now, in order for me to find this confidence value, what I do is I go to my normal tables and I look up 0.10 in the bottom or the left tail. Okay, now I'm not looking on the outside because the outside is the number I'm looking for. I'm looking for this shaded area on the inside. So I'm looking through here and I'm trying to get the closest I can to 0.10. Looks like I'm getting pretty close here. Ooh, look at right here, 0.1003. So if I trace back, that looks like negative 1.2, and then all the way up to the top would be 8. So that's going to give me a value of 1.28. Now, because I'm below the mean, it's a negative 1.28. Now, because of symmetry, I know I have the same value right up here, 1.28 above the mean. So remember, 1.28 is the number of standard deviations I am above the mean or below the mean to find this 80% confidence interval confidence factor. Now, the way that this will look, this is called Z alpha over 2. Okay? Now, the way this develops then, alpha is the amount, 0.20 in this case. If I'm 80% confident, that means the value or my lack of confidence is 0.20. So alpha is 0.20. I divide it by 2 here. And the reason I divide it by 2 is I have those two tails. So Z 0.10 in this case was plus or minus 1.28. So that's my confidence factor. Now it's going to be really important that you be able to find all sorts of different confidence factors. So we'll go over a couple others. And there are some ones that are very common that we use over and over again that we'll want to definitely make sure that we know. Let's go ahead and let's go for a 90%. Let's do these in order. So let's go ahead and develop the idea of the 90% confidence interval. So if we're 90% confident, that means we're willing to have 10% error, and this alpha is that error that we're willing to have. So in this case, alpha is 0.10. This is the standard normal distribution with a mean of 0 and a standard deviation of 1. Now, if I have 90% confidence interval, that means 90% of my area is centered above the mean. So I have 10% area left to distribute in the tails. Now, because I have 10% and I have 2 tails, I divide that by 2. So what ends up happening here is my Z alpha over 2 is Z 0.10 over 2 is Z of 0.05. So let's go ahead and grab our normal tables and let's look up 0.05 in the left-hand tail. Now remember, we're not looking for 0.05 on the outside, we're looking for 0.05 on the inside. This one's always easy to find because there's an asterisk here. It's halfway in between 0.0505 and 0.0495. So I'm going to trace this down, and it tells me that my z-score would be 1.645 because it's exactly in between. So my z-score here is 1.645. So I'm 1.645 standard deviations above the mean, and I'm 1.645 standard deviations below the mean. Now that's the value that I want to keep in mind for my 90% confidence interval. Now another common confidence level to have is a 95% confidence interval. Now you should be able to find any of these values. There's Z alpha over 2 for any level, but we're just going over some common ones. So if I'm 95% confident, I'm willing to have 5% error, so alpha equals 0.05. This is my standard normal distribution with a mean of 0 and a standard deviation of 1. Now for here, again, I have 0.05 over 2 for my alpha over 2. So this is Z sub 0.025. My mean is 0. I have 95% of my area. That means I have 5% of the area left to distribute between two tails. And so that's this 0.025 value is in my upper tail and then my lower tail. Well, this is all symmetric, so once I find one, I know the other. So let's go ahead and grab our normal tables again, and let's look up 0.025 in my lower tail. Okay, 0.025. Oh, it's right in here. Okay, so I have negative 1.9 and then 6. So that's telling me I have negative 1.96 standard deviations below the mean and 1.96 standard deviations above the mean. So my confidence factor, my z-score, my z-value, is going to be plus or minus 1.96. So we've done 80, which isn't actually used that common, but we've used 90, which is very common, 95, which is very common as well, and then we'll also look at 99% confidence. Now remember, if you are given any value, you should be able to find how to determine these z-scores or these z-values. We're for 99% confident, that means we're willing to be wrong 1% of the time. So alpha is 0.01 in this case. This is my standard normal distribution that I'm using. So Z alpha over 2, 0.01 over 2 is 0.005. And so that's what I want to do here using my normal tables in this curve sketch, is to find the area then of 1% split between two tails. So 0.005 and 0.005. So let's grab our normal tables. And we're looking for 0.005, and it's an asterisk on your normal table. So this will be easy to find. It's halfway in between negative 2.57 and negative 2.58. So my z-score here is negative 2.575. And if I follow this arrow down, here's that 2.575. And again, that'll be plus or minus, because I know from symmetry that I have a negative 2.575 when I have 0.005 in my left tail, and 2.575 when I have 0.005 in my right tail. So those are some examples of finding confidence factors, or z-scores. So we could make a quick table to summarize those. Now remember, you should be able to find these for any level of confidence. These are just some common levels of confidence that we have. So here's our, let's see how we want to organize this. Confidence interval, confidence level, I guess. This is for a two-sided confidence interval as well. So we looked at 90%, 95%, and 99%. And then we found the z-score that goes along with that. Now I want you to remember, since this says z-score, these are only based on the normal curve. So if we were using any other distribution, these numbers don't work anymore. These are only based on the normal distribution, and I know that here because of the letter z. So 90% was 1.645. Okay, and I'm just going right up here. Oops, here's 90%, 1.645. 95% was 1.96. And then 99%, which was 2.575. And then all of these are plus or minus because I have a positive and negative value. So these are z-scores that we use often enough that you'll want to have them memorized. Now, having said that, if you're given a problem that says, What if I'm 92% confident? You should be able to find that confidence factor, that z-score, using the methods that we did right up here with the normal table. Okay, so kind of working back toward the confidence interval, let's go ahead and start talking about the confidence interval for a population proportion. Now, the correct interpretation of a confidence interval is trying to come up with an interval that will capture the true population proportion. That usually means a percentage of some sort. So our confidence interval here will be p hat, and I'll explain what each of these variables means, p hat plus or minus our confidence factor, z alpha over 2, and then this is the standard error of this statistic, and it's the square root of p hat, q hat, and q of course is 1 minus p over n. All of this is underneath the square root sign. So let's go ahead and talk about each of these. P hat is the point estimate. Remember, the point estimate is a statistic that estimates a parameter. It's the point estimation of the population proportion P. So first of all, P hat is a statistic, and the population proportion is given by this script P, and it's usually given as a percentage or a decimal. So P hat is the statistic based on a sample, and P is going to be the parameter, and it's based on a population. So this will be definitely a formula that you'll want to know. P hat plus or minus my confidence factor times the standard error of the population proportion, or sample proportion P hat. Now, one thing that we didn't mention here was Q hat. Q hat is just 1 minus P hat, the same as it was for the binomial distribution. P is equal to just 1 minus Q. Q is equal to 1 minus P then. So let's go ahead and start by building a confidence interval for our next example. Okay, let's go ahead and suppose a random sample is used to estimate a population proportion P. We want to go ahead and build a confidence level of 95%. So suppose we have a sample of 500, and I have x is equal to 400, and I'll explain what this means here in a moment, and I want to be 95% confident. So I went and sampled, let's say, 500 people. 400 responded as I was keeping track in the affirmative. So let's say I was going through and I was asking something about, do you plan to graduate within the next 3 years? 400 out of the 500 students I sampled said yes. So what I want to do, I didn't sample the entire student body, I only sampled 500. So I want to come up with an estimate of the true proportion of students who plan to graduate within the next 3 years. So I can calculate P hat. P hat is 400 over 500. Now if I wanted to do the proportion of students who are not planning on graduating within the next 3 years, I would have 100 over 500. So we have to keep track of that. Q hat then is 1 minus 400 over 500, which is 100 over 500. And then I have my confidence factor here, my z alpha over 2. Well, this is z. If I'm 95% confident, that means I'm willing to have 5% error, z 0.05 over 2. If we look up on our table, again, that's 5% in the lower tail. I can see down here it's negative 1.645. So that's, whoops, I did that wrong. My confidence factor then is, I'm 95% confident, so 0.05 divided by 2 is 0.025. I was looking up the wrong value. So 0.025 would be plus or minus 1.96. There it is. So 1.96. So let's go ahead and build that confidence interval now. The general form for the proportion is p hat plus or minus z alpha over 2, p hat q hat over n, and this is all square rooted. So again, this is my point estimate, this is my margin of error. So as I'm building this, my point estimate was 400 over 500, and we don't want to do any rounding until we're completely done. This could certainly be reduced, but we don't want to have to round it. Plus or minus my confidence factor of 1.96 times the square root of p hat, q hat over n, and n was my sample size. So there's a lot going on here. Okay, so now 400 over 500, that's going to be 80% or 0.8. So when I start building my confidence interval, again, I don't want to round to the very end. Plus or minus, and now I need to take all of this and put it together. Now the thing to remember here is this square root goes over all of this. So you want to go ahead and calculate all of this on the inside and then take the square root. So let's go ahead and look to see what that will be on our calculators. So it would be square root, and I have a fraction key on mine that's under alpha y equal if you want to see if yours has that. That would be 400 divided by 500 times 100 divided by 500, and in the denominator you'd have 500 then. Now if you don't have this nice fraction option, just make sure you put parentheses around everything to make sure that it's calculated correctly. So this value, the square root value, is this 0.01788, etc. Now if I take this number times 1.96, that's going to give me my margin of error. So what I get here then is this 0.0350615,459, and we don't need all that, but it's a good start. So I get 0.80 plus or minus, let's go ahead and go to 4 decimal places, 0.351. Okay, so this is my point estimate of the true population proportion of students who are going to graduate within the next 3 years, so about 80% from my sample. So this is my point estimate, and this is my margin of error. Now to find my confidence interval, my left endpoint would be 0.80 minus 0.0351, because it always goes smallest to largest. And my right endpoint would be 0.80 plus 0.0351. That's my upper limit. So let's go ahead and find that actual confidence interval. 0.8 plus 0.0351 be 0.8351. And then, oops, I did my upper there. Let's do our lower. Let's do 0.8 minus 0.0351. That gives me 0.7649 as my lower bound, and then my upper bound would be the one I just found, was 0.8351. So I can be 95% confident that the true proportion of students who plan to graduate within the next 3 years is between 76 and 84% about, if we round that to the nearest percentage. We just need to be careful about how we follow directions in my math lab about rounding, so make sure you keep a close eye on that. Let's go ahead and look at another example. Actually, I'm going to give you one other way to write this first. Sometimes when you're working, you'll see this written as 0.7649 less than p less than 0.8351. This means the true population proportion P is between, we hope, we're 95% confident, this captures between 0.7649 and 0.8351. So what we were looking at here is the number of successes, people who are going to graduate within the next 3 years. Okay, so we count that as a success, and then we kind of work backward from there. Let's go ahead and look at another example. In this example, let's go ahead and suppose we have a sample of size 500. And let's go ahead and go this time with 20% successes. So we're not given the number, we're given the count. And we want to be, let's say, 90% confident. So we asked 500 students if they were going to purchase a new cell phone within the next year, and 20% said they were. Okay, so this is going to be our value for p hat. It was given to us outright. We didn't have to calculate it. So this is p hat. So let's go ahead and look at our form for our confidence interval for a population proportion. P hat plus or minus z alpha over 2 p hat q hat over n. So when we're starting to work here, we need to identify some values. First of all, p hat again is 0.2. Z alpha over 2 for a 90% confidence interval was 1.645. And again, if I'm 90% confident, that means I have 5% error in either tail. If I look up 0.05 on the inside of my table, I can follow this down, and I get plus or minus 1.645. And then my standard error. So this would be 0.20 is p hat, q hat would be 1 minus that, and this is all over my sample size of 500. So this would be 0.20 plus or minus, and then let's go ahead and calculate my margin of error. Now again, the margin of error includes this confidence factor of 1.645. So I'll calculate this all in one big step now. 1.645 times the square root, and this time I'm not going to use my nice fraction button just in case you don't have one, so you can see how to work this. 0.2 times 0.8 divided by 500. So I get 0.0294. Let's go ahead and round this to 4 places. 0.0294. Okay, so this is my point estimate. This is my margin of error. And let's go ahead and come up with my confidence interval. Now confidence intervals always go from smaller number to larger number. So I'd take 0.2 minus 0.0294, and I'd get 0.1706. And then I'd take 0.2 plus 0.0294, which is 0.2294. So this is my confidence interval. Now again, you might see it written like this. The true population proportion is between 0.1706 and 0.2294. Now my hope is that that true proportion that's out there, I hope that this confidence interval captures it. Now what ends up happening if I were to build 100 of these intervals based on the same sample size, the 95% portion comes in to say 95% of the time, 95 out of those 100, I will capture the true mean, 5 I will not capture, and I hope this is one of those that does the actual capturing of the true mean. So that's kind of the interpretation that we like to look at there. Now sometimes what we want to know is how many do I have to sample in order to come up with a particular margin of error. So these we work backward, and these are called sample size determination problems. So for instance, if I was doing some sort of a survey based on an upcoming election, I might say, well, I want to be 2%, plus or minus 2%, for my margin of error with a 95% confidence. How many people will I have to go ask? So these are the types of problems we like to work backward. So what we have here then is we have a sample size determination. Now what we do is we take the margin of error and we work backward. So these are the formulas, and if you want to work through that algebraically, you can. This is going to look like z alpha over 2, and this is going to be squared. And again, you can verify this if you want algebraically by taking this formula up here and setting it equal to e and solving. And this is going to be over E, which stands for my margin of error squared. So this is my sample size determination formula, and this will hold true for p hat, any q hat. Now my margin of error is given as a decimal, so if I have a 3% margin of error, that should be 0.03, and this confidence factor is my z-score. Now I have a different formula that I use under particular circumstances, and I use p hat q hat if I don't have an estimate for p hat, meaning I don't have an idea of what p hat could be. What I end up doing here is I end up trying to maximize the number of people I'll have to select by making each of these equal to 1/2. So 1/2 times 1/2, this is squared, is 0.25 all over e squared. And this I use if p hat is unknown. That means you don't have an estimate to go after. Now if I have an estimate for p hat, then I use this formula up here. Now my big rule for both of these, always round up. So if we talk about always rounding up here, what if I have n equal 123.7? Okay, well that's obvious. I round this up to 124. What if I had n equal 231.1? Well, I have to round this one up as well, because if I round it down, I won't have quite the number that I need to achieve a particular margin of error and a particular level of confidence. I'll be slightly under that. So again, you always round up to the next integer for any of these sample size determination problems. Let's go ahead and work some of these as an example. So let's go ahead and use the information below. And we're going to use this information below to find the minimum sample size required. Now also here we're talking about a proportion of a population. These formulas will change depending on what I'm trying to estimate. So use the info below to find the minimum sample size required to estimate a population proportion. And of course a proportion, if we talk about 0.05, that would be 5%. And so this could be also translated to percentage as well. Okay, so the information that's provided, we want our margin of error to be, let's say, 8%, so 0.08. We want our confidence level to be 95%. And then for our first example here, p hat and q hat are unknown. So because p hat and q hat are unknown, I'm going to be using this formula up here. So let's go ahead and grab our formula and then we'll populate it. So we have our z alpha over 2 quantity squared. 0.25 comes directly from the formula, and then e squared in the denominator. So for our example, z alpha over 2 has to do with this 95% confidence factor. So if I'm 95% confident, that means I'm willing to have 5% error or be wrong 5% of the time. Now if you want to, you can scroll up and look at that table we produced, or this is 0.05 divided by 2 is 0.025. And if we look on our normal tables under 0.025, what we're looking at here then inside the tables is 1.96. Now it doesn't matter if we use a positive or a negative value here, because when I square it, it'll become positive. So positive or negative doesn't matter. E is 0.08 quantity squared. So let's go ahead and crank this in to our calculators and see what we get. So in my numerator I have 1.96 quantity squared times 0.25, and then in my denominator I have 0.08 squared. So what I get here is 150 point, whoops, let's see what happened to that, 0.0625. Now remember, our rule for sample size is always round up. Now I'm not rounding up because of the 6, I'm rounding up because this is slightly larger than 150. So for sample size determination, always round up. So therefore, we would sample 151 people. Okay, so notice I still don't know the population, so this has nothing to do with how large the population is. It has to do with the amount of error and our confidence factor that we're willing to have, and we always round up. Let's go ahead and do the same type of problem. So use the info below to find a minimum size sample required to estimate a population proportion. Now this one, we're going to be given an estimate for P. And if we know P, we can figure out Q as well. If we know P hat, we can figure out Q hat. So for this particular example, margin of error is going to be 4 percentage points. So they're going to give this information a little bit different. So margin of error equals 4 percentage points. Confidence level, let's say, is 90%. And we're also given that from a prior study or some other background, we know P hat is equal to 0.52 or 52%. Let me make that look like a 5. Okay, so we go ahead and write down our formula. P hat plus or minus Z alpha over 2. P hat Q hat over N. Whoops. That's the formula we'd use for the confidence interval. We're looking at sample size determination. So let's get that correct formula. So that would be N equal Z alpha over 2 quantity squared P hat Q hat over error squared. So Z alpha over 2 for a 90% confidence factor, that would mean I'm willing to be wrong 10% of the time, and I'd split the area between the tails, so I'd have 0.05 in my lower tail. So 0.05 we can see is directly in between 1.64 and 1.65. So reading down here, I get that 1.645. Now in this case, we know what P hat is, so we can put that in as 0.52. And now if P hat is 0.52, Q hat is the complement of 1 minus 0.52, then is 0.48. Margin of error is 0.04. Quantity squared. So this is squared up here with our Z as well. So let's go ahead and plug this into the calculator and see what we get back out. So in the numerator we have 1.645 squared times 0.52 times 0.48 divided by, and we have 0.04 squared in our denominator. So it looks like we end up with 422.1399. Now remember, we always round up, so therefore we should sample 423 people. Now this could be other things too. It could be light bulbs or cars. I'll just use people as this example. So just like we did, we rounded up here. We're going to round up. So we always round up when we're talking about sample size determination. So we're good at finding our z-scores. We're good at building a confidence interval, finding that point estimate and margin of error. The next thing we need to look at is to being able to apply this to some sort of a problem. Now usually with a problem, you're given some information, and then we look at the value of our confidence interval to see if that information is supported or not. So let's go ahead and take a second to write up a problem, and then we'll try and solve it. So for this example, we have during a period of 11 years, 696 of the people selected for grand jury duty were sampled, and 74% of them were immigrants. We want to use the sample data to construct a 99% confidence interval estimate of the true proportion of grand jury members who are immigrants. So this value, 11 years, is kind of a red herring. We're not going to need this. Now there's a second part to this question, but let's go ahead and construct the confidence interval first. So to get started, let's go ahead and look at our p hat plus or minus z alpha over 2, standard error p hat q hat over n. And then let's go ahead and find these values. So p hat they give us. P hat is equal to this 74% up here, so that's 0.74. And then q hat is the complement, so that would be 0.26. Now n is our sample size, in this case 696. And again, this 11 is a red herring. We actually don't end up using it. Now the other thing that we have here is our z-score. We need our z alpha over 2. Now our z alpha over 2 is based on this 99% confidence interval. So my alpha is 1, and I have to split the 1% between the tails, so that would leave me with 0.005, and this is that special case down here of plus or minus 2.575. And again, these values are also on the table that we did earlier in the notes. So now I go ahead and populate this. P hat is 0.74 plus or minus 2.575. We have our square root 0.74, 0.26 is my q hat, and then n is equal to 696. Okay, so my point estimate is 0.74. And then let's go ahead and calculate our margin of error. So for our margin of error, I basically put in everything after the plus or minus sign. So I have 2.575 square root. Now I have to be careful how I put this in. 0.74 times 0.26 divided by 696. Now this is going to give me my margin of error of 0.0428. Now usually there'll be some directions about rounding, so we want to let's round this to 3 places. So for our left endpoint, what we'll have here then is 0.74 minus 0.0428. And then for my right endpoint, it's 0.74 plus 0.0428. It always goes from the smaller value to the larger value. So let's go ahead and have a look at our smaller value. That would be the 0.74 minus 0.0428. And I get 0.6972. And then for my larger value, that would be 0.74 plus 0.0428 is 0.7828. Okay, so here's my confidence interval, and remember it always goes small to large. Now another way that we'll see this written is between the interval using our population proportion. Now if I round this to 3 places, this would be 0.697 less than p less than 0.783 rounded to 2 places. So this notation basically means between. So this is our confidence interval. And in particular, it's our 99% confidence interval. So the interpretation of this is I'm 99% confident. Okay, so this means if I produce this interval 100 times, 99 of the intervals I produce would capture the true proportion. 1 wouldn't, and I hope this is one of the 99 instead of the one that didn't capture. Now we're going to answer a question based on this interval. Now the question is, given that among the people eligible for jury duty, given that among the people eligible for jury duty, let's say 69.9% of them were immigrants. Okay, so that means out of the population that could have been selected for jury duty, 69.9% were immigrants. Does it appear that the jury selection process was biased toward immigrants or biased against immigrants? So does it appear that the jury selection process was somehow biased against immigrants. So let's do a couple things here. What if 69.9% of my population was immigrants and only 10% showed up on the jury duty? Let's say 5 to 15 was my confidence interval, 5 to 15%. We could say, well, wait a minute. On my jury duty, my grand jury duty, only 5 to 15% were immigrants, but the population is represented by almost 70% immigrants. That would definitely show some sort of a bias. But if we look at 69.9, it falls in this interval, not by much, because this is 69.7 here, but 69.9 does fall in this interval. So what we would say here then is we would say no. So remember the question, does it appear that the jury selection process was somehow biased against immigrants? And we're going to say no. And the reason why is the confidence interval, the CI stands for the confidence interval that we have here, includes the true percentage or proportion of immigrants. So again, 69.9% lies in this interval, so I'd have to say no, it doesn't appear that there's any bias against immigrants. So as you're working through these problems, you're going to sometimes be asked some questions like this, and this is really the true application of statistics here, is to be able to infer something. So it's very important that this part is understood really clearly. As usual, if you have any questions, please bring them to class. Stop by my office hours. The Math Assistance Center is open as well. And if you have any questions, make sure you ask so we can help you out. Good luck.